Next we will talk about the ligand isomerism. Ligand isomerism. That means what? This isomerism occurs due to the isomerism in the ligand. For example, if I say, let's say nickel, if I say +2 over here, this is a square planar complex. Let's say it is a NH2, it is a CH2, it is CH2, it is CH2. Let's say it is a NH2 like this. And if I say NH2, let's say it is like this, CH2, it is CH2, it is NH2 like this. Let's say it is a square planar complex overall +2. So this is basically 1 2 3, that is 1 3, we can say propane 1 3 diamine. This is basically propane 1 3 diamine, and it is ethane 1 2 diamine or ethylene diamine. So in this case, if I want to make the complex like this, nickel +2 over NH2, it is coordinate bond. Let's say again square planar complex. I am talking about, let's say CH2, it is CH, it is CH3, and I am taking NH2 over here. Quite naturally, I can get the ligand isomerism, because in the ligand I have made the isomerism. It is basically NH2, it is like this. So you understand that here it is 1 2 3, that is propane 1 2 diamine. This is basically propane 1 2 diamine, propane 1 2 diamine, and it is basically propane 1 2 diamine, and it is propane 1 3 diamine. So obviously the complex having different ligand, and the ligands have that isomerism, so therefore it is a ligand isomerism, we can say. Next, if we talk about the coordination isomerism. So in that case, basically it is happening between two coordination spheres. For example, if I say Cr H2O6, and let's say it is your CO Cl6. If I write this, and if I write Cr H2O5, it is your Cl, and it is your CO, it is, let's say Cl. I should write a Cl first. I should write Cl first. Cr Cl. It is H2O5, and over here CO Cl5. It is H2O. In that case, you can see that one water molecule is coming from here to here, and one chlorine coming to here to here. So this way we can write CO basically H2O6, and finally CrCl6. Therefore what, there are several isomers you can get. Overall it is 0 plus 3, overall it is minus 3, and whole charge is 0. That means what, 6 water molecules can come over, 6 chlorine at the most can come over here. So therefore 6 coordination position isomers are possible in this case. Coordination isomerism is possible. 6 coordination isomers are possible: H2O5, H2O4, H2O3, H2O2, H2O1, H2O0. So this way we can get total 6 coordination isomerism possible. Now if I talk about coordination position, for example, if I say, let's say it is your let's say I'm saying C5H5, let's say C5H5, that is eta 5 basically cyclopentadienyl anion, and with this let's say I'm taking C5H5 twice. Let's say it is a C5H5, and then let's say H2O, it is your H2O, it is your like this. So in that case we can get 6 electron pairs have been given. So let's say I'm taking a simple case. Let's say for the coordination position isomerism, it should be a complex which is basically bridge complex. For example, if I write H2O4, let's say H2O4 Cr, let's say NH2, it is your, let's say OH, it is your CO, let's say it is your NH3, it is your 4, it is your like this, it is your plus 2. So this, if I say, and along with this if I write Cr, let's say CO, it is your H2O4, or I can say Cr, let's say Cr over here, it is your H2O thrice, it is your NH3, and over here I'm writing over here Cr, and it is your NH2, it is your OH, let's say it is your CO, it is your basically NH3, it is your H2O, it is H2O, it is NH3 thrice, let's say NH3 thrice, and this, and it is like this. So overall charge, how much you should calculate? chromium is plus 3, I mean to say over here, and cobalt is plus 3. So NH2 is minus 1. All this is 3 to 6 minus 1, it is plus, and also which is minus 1, so it is plus 4 basically, and over here it is also plus 4. So just look at the question, example 1 and example 2. Just over here, since this is a bridge complex, the bridging ligands are basically over here, NH2 and OH are the bridging ligands. So over here NH2 and OH bridging ligands is same. Only thing is that the environment of the chromium over here, from 4 water molecules, it is becoming 3 water molecules and 1 ammonia, and here 4 ammonia were there, and here 1 H2 molecule has come into the picture. So therefore we can say that this is basically coordination position isomerism. Coordination position isomerism only occurs when it is when basically there is a bridge complex actually formed. Suppose for example, what is the name of this complex? If I say, then it is triaqua, it is amine. So amine should come first. So I can write the name of the complex will be amine triaqua, amine triaqua, chromium. It is your chromium, it is your 3, chromium 3, and then mu amido, mu hydroxo. So I should write mu amido should come first, A alphabetically, mu amido and mu hydroxo. Then again we can say 3 ammonia molecules and 1 aqua molecules is a triamine. We can write mu hydroxo, chromium 3, and mu amido, mu hydroxo. Then we can write triamine, it is aqua, and then cobalt, it is again 3, complex. So it is cobalt plus 3. I am talking about chromium is plus 3 because we know cobalt can be having plus 2 and plus 3, chromium can be plus 3 and plus 6. So with this I will conclude the coordination position isomerism. So next we will talk about the polymerization isomerism. Polymerization isomerism. What is that polymerization isomerism? We don't find it in organic chemistry, but here in coordination compounds we find that. For example, PT, let's say NH3 twice, PT NH3 twice Cl2. This is a complex. There is a complex where platinum is plus 2 and overall charge is 0. But if I write PT NH34 overall plus 2 and PtCl4 overall minus 2, so you can see that both the platinums are plus 2 state, and this is just dimer, or that you can say twice of this molecular mass is this molecular mass. So it is dimer, almost it is exactly dimer of this complex, and so that is what we call say polymerization isomerism. So therefore what, dimer, trimer, tetramer, like this we can say the polymerization isomerism, because the molecular mass over here, if I say M, it will be basically molecular mass will be 2M, and this way it is called polymerization isomerism. Now with this I will finish the structural isomerism part. Now we will go to the stereoisomerism. Stereoisomerism. In this case, first I will talk about geometrical isomerism. In the case of geometrical isomerism, just look at, see, if it is tetrahedral molecule A, let's say B, let's say C, let's say D. If I talk about it is tetrahedral molecule, there cannot be geometrical isomers possible. Geometrical isomers is not possible for tetrahedral molecule. But if I talk about a square planar complex in 4 coordination, let's say M A, let us say B, let's say C, let's say D. Yes, there is a possibility of that geometrical isomerism. How it is possible? Let's say A is trans to D. So in the other complex we can write A is trans to B, and another molecule you can say A is basically trans to C. So over here, let's say it is D, let's say it is B. Try to understand that A trans D, A trans B, A trans C. So therefore 3 geometrical isomers we can get, because we can understand that A trans D, A trans B and A trans C. So in terms of trans, if we can position the ligand, so we can see the number of geometrical isomers. Yes, suppose if I talk about simple complex, let's say let's say A is a complex, let's say. In this case, all the ligands are same. So of course there will be no geometrical isomerism. If I say again AMA3B, of course there will be no geometrical isomerism. If I say AMA2BC, then yes, geometrical isomerism will happen, because B trans A and next one will be B trans C. You can see it is a B trans C and it is a AA. In this case, A cis A, A trans A also is coming out. So therefore, there will be 2 GI possible for AMA to BC type of complex. AMA to BC type of complex, you can say 2 types of geometrical isomers are possible. And for your information, the square planar complexes, unless the ligand has the optical isomerism, the square planar complex cannot have optical isomerism, optical activity, because this complex is optically inactive. Why optically inactive? Because there is a plane of symmetry, the plane in which they are basically existing, there is plane of symmetry present. So they are optically inactive. So I am taking instead the geometrical isomerism, optical isomerism 2. But if it is tetrahedral molecule, let's say tetrahedral complex, let's say it is tetrahedral molecule complex, yes, there can be optical isomerism, but it is very difficult to find out the optical isomers or trap the optical isomers for the complexes. But yes, tetrahedral complex should show the optical isomerism because it doesn't have any plane of symmetry. One of the example is zinc glycinate. Glycinate, this is basically overall 0. It is called, it is optically active. It is optically active, and you can see that this basically, we can say that this complex is basically inert metallic complex, because overall charge of the complex is 0 as shown in the figure. The zinc glycinate optically active. How we can show that? Let's say zinc over here, it is your NH2, let's say it is CH2, it is C double bando, let's say it is O minus. Over here it is basically tetrahedral, I mean to say it is tetrahedral like this. And over here, let's say it is your O minus, and over here, let's say it is your O minus, it is your CH2, C double bando, it is your CH2, it is your NH2. So this is nothing but there is no plane of symmetry. You can see that of course this is optically active. We don't have any plane of symmetry in the molecule. So zinc glycinate in the being the tetrahedral complex, it is a tetrahedral complex, so optically active. Zinc glycinate has been found to be optically active. Generally, it is very difficult to isolate the tetrahedral optically active molecules. Optical activity arises. Why? Optical activity occurs due to number 1, lack of plane of symmetry, and number 2, center of symmetry, lack of center of symmetry, as we found in the organic chemistry. So these are very, very important. Why compound is optically active, why compound is not. So tetrahedral complexes should be optically active, but it is very difficult to isolate. But hence we are finding a geometrical isomerism in which square planar geometry cannot show optical activity, and geometrical isomerism can be shown by AMABCD type complex. It can be AMA2BC type complex, not by AMA4 or AMA3B. So therefore, with this, I will conclude the geometrical isomerism with tetrahedral coordination or square planar coordination, that is 4 coordination. I am finishing over here along with the optical activity.